Section 2, we're going to look at two formulas that use the radian measure of an angle rather than degree measure of an angle as part of the formula to make the calculation. First one you can see here is called the length of an arc. To find the length of an arc on a circle, use the formula S equals R times theta. S is the length of the intercepted arc. R is the radius of the circle. And theta is the central angle in radians. So there is the key phrase there, central angle in radians. Let's try here a quick sketch. I'm not going to be able to draw a very good circle with this thing, but we'll make do. So what we're finding here, the length of the intercepted arc. Obviously, we all know what the radius of a circle looks like. So our intercepted arc is going to be out here on the outside of the circle somewhere, and then right in here in the middle, right in here, this is the theta. That angle theta is going to be measured in radians rather than degrees. Okay, so we must be able to use those conversion factors from section 1. Also important as we move through here, even more so as we look at other formulas, but labeling becomes more the process here than anything else. One more time, S is the length of our intercepted arc, so S is out here on the outside of the circle. R is the radius of our circle. We all should be very familiar with the radius, and theta is our central angle in radians. So jumping down here, what is the length of an arc intercepted by an angle of pi over 3 radians on a circle with 9-inch radius? Everything's pretty well spelled out here. What is the length of the arc? There's our S. Our angle, pi over 3 radians. There's our angle in radians, our theta. And we have a 9-inch radius. There is the R. So S equals R times theta. You can see in this case we're trying to find S. So S is going to equal the 9-inch radius times the pi over 3. I'm going to go ahead and write it out this time. But we probably won't write this out very often. I made a comment about this earlier in one of our other sections, but radians is considered to be a non-label, so when I multiply inches times radians, my label is going to stay as inches. And 9 times pi over 3 radians gets me about 9.42 inches as the length of our intercepted arc. As I mentioned previously, conversions, changing one label of measure to another is a big part of this section. So I have a handful of common unit conversions. There are 5,080 feet in a mile, 1 minute is 60 seconds, 1 revolution is 2 pi radians, 1 foot is 12 inches. Now this is by no means an all-inclusive list. Well, these are unit multipliers, meaning these two numerator and denominator have the same unit of measure, but they are measured in different forms. They mean the same thing. 5,080 feet is 1 mile. So if I were to multiply by this fraction, I'd be multiplying by 1, which doesn't change the value, it just changes the form or the label here. And you'll see that illustrated here in our next example. It says a car wheel has a radius of 11 inches from the center of the wheel to the road. How many revolutions must it make to travel 2,000 feet? Let's start out here. Radius, pretty well spelled out, R. Travel 200 feet, this is how far it's gone, or this is the length of our arc. And our revolutions we can eventually measure as theta. We'll probably start out as radians or degrees and move from there. So we have some labeling to do here. S equals R times theta. In this case, we know S is 200 feet. We know our radius is 11 inches, and we're trying to find theta, or our central angle. So the first thing you probably notice is on one side we have a label of inches, the other side we have a label of feet. We can't, if it were an algebra problem without the labels there, we just divide both sides by 11 to solve for theta, get theta by itself. But because we have different labels, we have to have the same label. So on this side, on the left-hand side, I'm going to put up a unit conversion, and with my fraction, I want to cancel the label of feet. So feet have to go here. I want to change it to inches, and for that to be a unit multiplier, I hope we all know that 12 inches equals 1 foot. I say unit multiplier, so now I've multiplied my 200 feet times a value of 1, but I've changed the label. 12 inches is the same thing as 1 foot, so I'm multiplying by 1, just changing what the label looks like, because between numerator and denominator, the feet now label will cancel. So on the left-hand side, 12 times 200 is 2,400 inches. That equals 11 inches times theta. So just a little quick manipulation to change my labels. I hope we would all agree that and to solve for theta, we divide both sides by 11 inches. And when we do that, that will give us theta equal to 218.18. Now the label on that, let's look over here. I divided 2,400 by 11 to get 218.18, but when inches is divided by inches, those are going to cancel, so I don't have a label left there. So my unwritten label, as we've talked about earlier, is radians. Now if you recall, our problem asked to find how many revolutions, not how many radians, so I have yet another unit conversion to make. I need to change my radian label over to revolutions. So I'm going to set up my unit multiplier here. I want to cancel the radians label. But radians is my denominator. I want to change it to revolutions. This has to have a value of 1. So from up above, 1 revolution equals 2 pi radians. You can see the label of radians then canceling between numerator and denominator. Now as a side note, I'm going to rewrite this. Theta equals 218.18 times 1 revolution over 2 pi. So we're dividing by 2 pi. As you type this into your calculator, be careful with that, because when you divide by 2 pi, your calculator, if you don't type in with parentheses, your calculator will divide by 2 and then multiply that quotient by pi, which will give you a completely incorrect answer. In this case, our correct answer is 34.72 revolutions. So again, just be careful with the order of operations on your graphing calculator. Put the 2 pi in parentheses anytime you divide by a product. You don't want to divide by the first term and then multiply by the second term. You want to divide by this product. Let's move on and see what else we have here. So the minute hand of a clock is 6 centimeters long. How far does the tip move in 40 minutes? How far is our S? Minute hand is 6 centimeters long. There's our radius. In some way, shape, or form, we're going to make this 40 minutes into our theta. So S equals R times theta. Trying to find S. Our radius is 6 centimeters. And again, somehow that angle is going to be theta. So 40 minutes is 40/60ths of an hour. If I take that times, I'll go the easy route for now for us to think. All the way around a circle is 360 degrees, so 40 minutes is 40/60 of 360 degrees, or 240 degrees. Now, eventually, I'd like us to be able to think in terms of radians. So by shortcut version, I could take 40/60 as times 2 pi. And when I take that times 2 pi, let's see the simplifying here. Calculator would probably be just as easy. But I wind up with 2/3 here. So I wind up with 4 pi over 3 radians. I'd have to multiply this one by pi over 180, which would give me the same thing. But as you can see here, our theta, or our central angle in radians, is 4 pi over 3. And now we can plug that into our calculator and get 25.13 centimeters as the length of our arc. Let's go through a couple more here. Pendulum is 5 centimeters long. This brings an arc of 120 degrees in 2 seconds. Find the distance the pendulum travels in 2 seconds. S, R, theta. So we're trying to find our S. Radius is 5 centimeters. Our angle is 120 degrees, but as we discussed on several occasions now, theta needs to be in radians. And if we recall our unit multiplier from first section, we're going to go ahead and multiply by pi over 180. And as I mentioned, I haven't shown this yet. I'll go ahead and show it now. We can simply type that straight into our calculator. No need to simplify that fraction. I take 5, maybe. Well, just take my word for it here. Apparently this is not going to work. So I'm going to go with 10.47 centimeters. Next problem here. Rotation of the smaller wheel in the figure causes the larger wheel to rotate. Through how many degrees does the larger wheel rotate? The smaller one rotates through 60 degrees. So this wheel here is making this one turn. So they're connected here, kind of like a pulley system or gear system, I guess I should say. So I'm going to find out how far the first one travels by saying S equals R times theta. And once I have that distance, I'll know how far the second one traveled, and I can work backwards to find my angle. So our first one tells me that I have a radius of 5.23 centimeters, and it rotates through an angle of 60 degrees. Well, once again, that angle has to be in radians. So I multiply by pi over 180. And when I do the math on that, it's going to tell me that my smaller wheel is rotating through an arc of 5.4768 centimeters. That's how far the smaller wheel has traveled. Now that means this larger wheel has traveled the same distance because it turns that one. So when I go to S equals R times theta for the big wheel here, I have 5.4768 centimeters is equal to the radius of 8.16 centimeters, and we can use it to find theta. Oh, you can see here we have the same unit of measure on both sides, so I can divide by 8.16 centimeters to find out what theta is going to equal. And when I divide by that, I get 0.67118. Notice the label of centimeters would cancel, so I'd have that unwritten label of radians. And once again, our information up here was in degrees, and it says through how many degrees. So I'll go ahead and convert this to degrees by multiplying by 180 degrees over pi, and theta is going to be about 38.5 degrees here. Let's keep pushing on. One more with our S equals R times theta. Radius of the Earth is about 6,400 kilometers. Panama City and Pittsburgh, Pennsylvania are located on the same north-south line. Panama City is located at 9 degrees north latitude and Pittsburgh at 40 degrees north latitude. How far apart are the two cities? Well, if you recall some of your social studies work, we'll get a quick little sketch here. We know latitude starts being measured at the equator, and the equator is 0 degrees latitude. So then it tells us that Panama City is at 9 degrees north latitude, so from here to here is 9 degrees, and that Pittsburgh, Pennsylvania is at 40 degrees north latitude. They're on the same north-south line, so if you think about the Earth or a globe or whatever, you can see it'd be a circular section that keeps going all the way around. We'll just do the part of it. But again, that angle from our equator up to Pittsburgh is 40 degrees. Now the radius of the Earth is not going to change from one spot on the surface to another. So the radius is 6,400 kilometers. And we can see we're going to try and find the distance between those two cities, or S. So if I jump over here, S equals R times theta. We're trying to find S. Our distance, or our radius, I should say, is 6,400 kilometers. I hope we would all agree that if from here to here is 9 degrees and from here up is 40 degrees, that our central angle in the middle is 31 degrees. So my central angle in degrees is 31 degrees, but it has to be in radians. So once again, we'll multiply by pi over 180. And if we do that, Panama City and Pittsburgh are about 3,463 kilometers apart. So that wraps up our little bit on the length of an arc. Several examples there. We have another formula here. Area of a sector of a circle. Area of a sector of a circle of a radius r bounded by a central angle theta, and intercept of the arc is 1/2 r squared theta. Area equals 1/2 r squared theta. We're talking about a circle. Once again, our central angle has to be in radians. Well, let's see if we can get a decent looking circle here. Not bad. What we're finding then here is maybe we took a piece of pi out of this and we're finding the area of that piece of pi right here. That's what we're finding. And one other side note to make is area is always measured in square units, whether it be square feet, square inches, whatever the case might be, but was measured in square units. So we're finding the area of a sector of a circle. Our angle has to be in radians. Radius is the radius of our circle, r is the radius of our circle, and a is our area. Jumping right into that, 10-inch diameter piece is cut in 6 equal slices. Find the area of each slice. So right there, that tells us what we're trying to find. That way we can differentiate between the formulas. If we have our 10-inch diameter, then we know that our radius is half of that. And we can use that information to find our area. So area equals 1/2. If our diameter is 10 inches, then our radius is 5 inches. So that's being squared. And if our pizza is cut into 6 equal slices, I'm going to show the degree measure over here. We could take 360 and divide it by 6 and get 60 degrees. Or I'm going to shortcut it. I could take 2 pi and divide it by 6, and that would give me an angle of pi over 3 radians. So that's what I'm going to use over here is pi over 3 radians. And all I have to do is plug that in and calculate using my calculator. And my area would be about 13.09 square inches. You can see when I square the inches, that's where the label of square inches would also come from. So one piece of pizza has an area about 13.09 square inches. Couple more here. The area or the on-ramp from a service street to a freeway is laid out as an arc of a sector of a circle. The radius is 720 feet. If the curve subtends or creates an angle of about 108 degrees, or is the area of the sector formed by the service street and the freeway. Once again, you can see that phrase, that question for the area. So area is going to equal 1/2. In this case, our radius is 720 feet. We're going to square that. Our angle is 108 degrees. We've been through this several times. We're going to have to convert that to radians by multiplying by pi over 180. That will give us the area of the sector of our circle. We cannot forget this unit conversion. That angle must be in radians, and that area is 588,500.5 square feet. Oh, we have one last problem to go through here to finish this section. Right here at the top. Windshield wiper of a car has a blade that is 16 inches long on the end of an 18-inch arm. If the arm rotates through an arc of 105 degrees, how many square inches of windshield are cleaned by the blade on each pass of the wiper? So let's start kind of working backwards here. I'm going to work with a second statement. We have the blade on the end of an 18-inch arm. So my diagram here with a black line has an 18-inch radius. Now, on the end of that arm is the blade that's going to clean the windshield. So this blade in blue is 16 inches. Now as it rotates, this is going to be, I don't know how good this is going to be, but as it rotates back and forth and cleans the windshield, most of us probably realize on our car that this little area down here doesn't get cleaned. It stays dirty. Right? In other words, to find the area, we're going to find the area of the entire sector. So 1/2 of 18 inches squared times 105 degrees multiplied by pi over 180. But from that, we're going to subtract the area not being cleaned, and that area not being cleaned has a 2-inch radius, the same angle, and that will give us the area that is being cleaned. So the area of the entire part minus the area not being cleaned, which in this case is going to be 293 square inches approximately. And that concludes our second section.